I know. Okay, let's begin. Yeah. All right. It's wonderful to see this great crowd of folks after dinner break. This is the first QBarm seminar of the winter quarter. I think we have a great lineup of us. I'm Ben Benma, and I'm very pleased to have as our first speaker this quarter with Fuchs here. So this is a personal friend of mine who I met when I was a grad student, first year in graduate school. He was a postdoc at Caltech, and I was scratching my head like, what is this philosopher doing in this experimental group at Caltech? And then, of course, he's not a philosopher, he's a physicist. Of course, the physicist thinking the philosopher. It's very confusing, but we'll understand this by the end of the talk. Chris has taught me a lot over the decades about what is essential in quantum physics and how to think about it and properly, in my opinion. So let me back up and tell you who he is. Chris is a professor of physics at UMass Boston. He's been there for almost, about a decade, yeah. He's an expert in quantum foundations in light of the revolutions in quantum information. In fact, he did his PhD in quantum information in 95, 96 with Carl Caves, one of the heroes of early quantum information. And that might have been one of the very first PhDs. It was just right at the beginning of all of that revolution. Chris is famous for developing this thing called QBism. I'm not going to tell you what it is now. That's to be the subject of the talk, I presume. But he's been in many places in the intervening years. He's been a fellow at the Max Planck Institute in Garching, a senior scientist at Raytheon, at the Perimeter Institute, as a technical member staff in Waterloo. Bell Labs for many, many years. He was the highest paid philosopher in the world. So one of the great things about Chris is that he doesn't ignore experiments. So actually his time—
Oh, he does. He does.
His time at Caltech was actually in the group of Jeff Kimball, who was a consummate experimentalist. And it was actually on the paper that did the first legitimate quantum teleportation experiment. So that's really exceptional. He's a fellow of the APS Society. He's been quoted and mentioned New York Times, Wall Street Journal, Forbes Magazine, NPR, you name it. And I guess the most recent thing, and this is what I'll cap it off with, this year he was chosen by Vox Publications' Future Perfect 550 list with the title that Chris Fuchs is revolutionizing how we understand our quantum reality.
Thank you. Wow. How many of you have ever seen Jeff Kimball? Jeff is like this tall, literally like this tall. And why did I work on his experiment? Because he came to my office one day and he slammed his fist on the table and he said, "Fuchs, you need to earn your living here." So there experiment. It's great to be back at Stanford. I haven't been here, I believe, in 11 years. And I thought I'd start off my talk with just a little dramatic reading of what I know about Stanford that I thought I didn't know then, but Ben Lev just told me that I had told him the story that I was visiting last time. In 1906, the philosopher, the psychologist William James visited Stanford, and he wrote in his a little article where it starts off by saying, "When I departed from Harvard for Stanford University last December, almost the last goodbye I got was that of my old Californian friend, B." I don't know who B was. "I hope they'll give you a touch of earthquake while you're there, so that you may also become acquainted with that other Californian institution." James goes on to say, "Accordingly, when lying awake at about 5:30 in the morning of April 18, in my little flat on the campus of Stanford, I felt the bed begin to waggle. My first consciousness was one of gleeful recognition of the nature of the movement. 'By Jove,' I said to myself, 'here's B's old earthquake after all.' Sitting up involuntarily and taking a kneeling position, I was thrown down on my face as it went fortior I don't know what that word means. Shaking the room exactly as a terrier shakes a rat. I felt no trace whatever of fear. It was pure delight and welcome. Go it, I almost cried aloud, and go it stronger, he said to the earthquake. How many of your students? Oh, look at that. Well, if there are any of you at the end of this talk who say, go it and go it stronger, then I promise you I'd like to meet you. And we have research fellowships in my group at UMass Boston. Okay, so what I want to tell you about is something called QBism. Don't pronounce it QBism, pronounce it like the art movement, QBism. And what is QBism? Well, to an extent, it's just another damn interpretation of quantum mechanics. That's the base level understanding of QBism. It's another damned interpretation of quantum mechanics. As David Mermin said, quantum mechanics is the most useful and powerful theory physicists have ever devised. Yet today, nearly 90 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every year. None ever did. Well, I gave a lecture at one of the Enrico Fermi summer schools in 2017. And for that one, I decided, well, let me try to form a partial list of the interpretations of quantum mechanics. Everybody's heard of the Copenhagen interpretation. I put interpretations because if you follow the writings of any of the guys up at the top, Bohr, Heisenberg, Pauli, etc., you'll find that they all differ in some number of details. There's the hidden variable accounts of quantum mechanics. There's something that's out of fashion now called modal interpretation. People at times have thought that consciousness somehow causes collapse of the wave function, etc., etc. The list goes on. Many worlds interpretations taken up by Hawking and Everett and science fiction fans the world over. There's a long list. At the summer school, I pointed out to the students that in English, not all of them were English, English speakers, that in English we have the notion of collective noun. And you've all heard of a pack of dogs or herd of cows. There's some really good ones here. And I noticed one relevant to standard architecture today. Architects. And I challenged the students at the summer school to try to find a good collective noun for the quantum interpretations. And the prize was that the one with the best proposal would go beer drinking with me. So they had a lot of fun. The winner was bullshit. But look at this list. I said no room for title on this page. You might think that, well, you look at all of that, that must be pretty flippant work. But look now at ones in the blue: Bohr, Heisenberg, Pauli, De Broglie, Wigner, Josephson. All of these people have Nobel Prizes in physics, and maybe one day someone from the many worlds camp will win the Nobel Prize as well. Science fiction fans have got it. But there must be something serious about this issue if you see these great founders of physics striving to get a handle on what quantum mechanics actually means. On the other hand, just by the very fact that the prize winners are in this list and how many of them have differing points of view, you get the sense that it's not productive work to be done, and that students would be better off shutting up and calculating and not thinking about these things at the basis of quantum mechanics. That phrase, shut up and calculate, was due to David Mermin, who, now many of you are young and won't know that he wrote for Physics Today for years and years, was a great writer of physics, and also Ashcroft and Mermin, the textbook that you probably do know of. David, when he proposed the phrase, he said when he was a student, he was told to shut up and calculate. But he said, I won't shut up. Because I think there are still things that we can learn by exploring these basic questions. Things about how our language was molded to thinking about classical physics but now we have to stretch it into a new machine. So anyway, David floundered on exactly which interpretation he wanted to follow himself until in 2012, he had a kind of epiphany and he started embracing this thing that I'm going to tell you about today, QBism, and he started advertising it. And I would say it's predominantly because of David's wide reach that QBism got any attention at all, and then that started a little cascade. And I would dare say that by now, QBism is one of the major interpretations of quantum mechanics, along with Everett and Bohm, and some things by Carlo Rovelli, and so forth. So I'm going to tell you about something current. It was 25 years in the making, but now we've had a little breakthrough. People pay something of attention to it. It took its start in an idea that comes from James, E.T. James, who you guys know because of the James Cummings model, but also he's known as being a great supporter of the Bayesian interpretation of probability. And he once had a faculty position here at Stanford. Stanford, I believe, did not tenure him, and so he left. But he left behind his desk, as I understand it. And Professor Mabuchi once had that desk in his office, if I recall correctly. So James said in some paper in the 90s, our present quantum mechanics formalism is a peculiar mixture describing in part laws of nature, in part incomplete human information about nature, all scrambled up together by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet we think the unscrambling is a prerequisite for any further advance in basic physical theory. I had been worried about what quantum mechanics was telling us many years before discovering this. But what I learned from James is that the way he saw it, quantum theory wasn't just about what the world is, but it's also in part about what we are and how we interact with the world. And he said they're scrambled together. And if you want to understand quantum mechanics, the thing to do is recognize that it's a mixture of these two things, and they need to be unscrambled. This was a big influence on me. It was an influence on Carlton Caves, his postdoc Rudiger Schock, and we took it seriously, this idea of unscrambling. You see, we were much younger then. In fact, this is roughly what I looked like when I first met Professor Mabuchi, who's not here. I was a little older when I met Professor Lev. We took the idea of Bayesian probabilities as the key. That if we could understand quantum mechanical probabilities as Bayesian probabilities, that would be part of separating the omelet. So we wrote this paper in 2002 that kind of got the ball. Was it 2002? Yeah, it was 2002. We had been talking about these things since 1993. It got the ball rolling. And the way it really got the ball rolling was that we started to recognize that taking this point of view had immediate explanatory power. So I'm going to go to lunch with some of you tomorrow, and at that point, I'm going to pull 3 coins from my pocket, and I'm going to show you how to do quantum teleportation for 75 cents instead of for millions and millions of dollars, because you can get the essence of the story already with the coins. You can understand that they're floating there. So it had an immediate explanatory power, and we found this very useful, and some of our colleagues found this useful. But it was just the beginning, and we started to understand that along with the immediate explanatory power, David also created new mysteries that needed to be sort of cleaned up. Ultimately, the requirement of consistency led us to a rather radical notion of Bayesian probability. One, not due to James, who didn't exactly subscribe to this flavor of it, but one to a man named Bruno De Finetti. And I just noticed this morning that look at his birth date, 1906, the same year as the earthquake here that we talked about earlier. De Finetti said, my thesis, in the beginning of the book, he writes, my thesis paradoxically and a little provocatively, but nonetheless, genuinely, simply this. And then he writes in all capital letters, displayed, probability does not exist. What he meant by that is that one should not think of probabilities as facts of nature. There's, what did I say, not factual features of nature. What am I trying to get at here? Well, if you think of probability as quantifying a degree of belief, then it's sort of rather obvious. So here, there's a point on the line that's targeted, and this is the real thing. This is the real thing that's out in nature. But this person may have some beliefs about what is the real thing in nature, and they capture that by a probability distribution of some shape. But a different person may have different beliefs about what is the fact of nature and write down a different probability distribution. So already there you get a sense that probability distribution is not the thing that's out in nature. What is really out in nature is the state of reality, this point. But in the Bayesian view of James, one of these guys is right and one of these guys is wrong, or maybe a third person is the right one. In other words, ultimately, there is a true distribution that describes where the fact is. And that is what we strive to know, the right information for describing the fact. De Finetti's version of Bayesianism was more radical. He said, if you look out in nature, there's nothing to justify this distribution that tells you it's right or wrong, except for this person here. It's right with respect to him. This one is right with respect to that person. If you wanted to like take the eye of God and find the right distribution, that's really the right one, he said there is no viewpoint from the eye of God. There is no viewpoint from nowhere. Well, to make our point of view consistent, we were led to this way of thinking like De Finetti. It had radical implications. Here's one of the radical implications. What do you do with quantum states? You calculate probabilities. We all know that. But we also know from quantum information theory that if we consider a robust enough set of measurements, and we talk about the probabilities for this robust set of measurements, from the probabilities, we can reconstruct the quantum state. So you could take the point of view that probabilities are first, and derivative of the probabilities are the quantum states. Probabilities imply quantum states. Well, this brought in the ghost of De Finetti, who might have said in the new edition of the book, my thesis paradoxically, a little provocatively, but nonetheless, is genuinely this, simply this: quantum states do not exist. If probability distributions are not factual features of nature, from this point of view, quantum states cannot be factual features of nature either. Now, I think Ben said something about me being a philosopher. How many of you can guess what the reaction of philosophers is to this point of view? They hate it, and they cry. Wah, you don't believe wave functions are real. That can't be right. Why can't it be right? Well, because my philosophy says it. They don't like it. So we've lost philosophers of physics. That's why they call me a physicist, not a philosopher of physics. But you know, Niels Bohr had the right answer. He said, I felt that philosophers were very odd people. They really were lost. Because they have not the instinct that it is important to learn something and that we must be prepared really to learn something of very great importance. He thought that they were just ignoring the opportunity to see the world differently than the philosophy they were born with or the professor taught them said it was. Okay, so I don't care so much that philosophers don't like this. But what's more troubling is that the vast majority of Bayesians are like the Ed James type of Bayesian, not the Bruno De Finetti type of Bayesian. And this idea that there's not ultimately the right information to specify the right probability distribution is kind of anathema to those kinds of Bayesians. And so they would say to us, you can't call your point of view quantum Bayesianism because you're no Bayesian. You're one of these loosey-goosey social democrats. Or something. So we couldn't really follow the word Bayesian in our V for QBism. But I don't know, maybe sometime around 10 years ago, I came across a letter from an old Supreme Court Justice, Oliver Wendell Holmes. He was writing to a friend. If I'm not mistaken, the friend's name was Einstein. But it's not the Einstein that you all know. It's just there are actually people named Einstein. He was writing to him and said, he mentioned this person, Chauncey Wright. He says, Chauncey Wright, a rarely forgotten philosopher of real merit, taught me when young that I must not say necessary about the universe, that we don't know whether anything is necessary or not. So I describe myself as a betabilitarian. I believe we can bet on the behavior of the universe in its contact with us. When I saw that, I realized that's actually the missing ingredient in what QBism was about. And we would be better called quantum betabilitarians. But that's a hard word to say, and it's rather ugly. So in the end, I just opted to say, well, look, QBism is just something new and sui generis, stands on its own. QBism is QBism. And the purpose of it is that it should be a metaphysical or conundrum, but also the basis for new physical questions, new physics. That was the hope. Remember the immediate explanatory power of the thing. So really the B stands for betabilitarianism, which is the missing piece of QBism, as I'll explain in a little bit, but don't bother to remember it too much. It's just Q and bism. By the way, I had a dog. My younger daughter wanted a dog and badly, but we already had a dog. And I thought, no, we can't have another dog. And then one day she came to me and she said, I see the perfect dog online. If we got him, I would name him Q. And you can give him a middle name. And I'm like, well, what middle name? She goes, anything you want to call him. I was like, how do you spell Q? Q-U-U-E? She goes, no, just the letter Q. And I was like, and I can give him the middle name. So we had a dog. Q was the first name. Bism was the middle name. He's still around. He's 9 years old. Okay, so here's what I want to do for the rest of the lecture. I want to tell you a little bit more about guts. What's the phrase? Nuts and bolts. Not the guts and bolts. The nuts and bolts of QBism. From that, I then want to derive a new expression for the Born rule that maybe most of you aren't familiar with. At most, Professor Leg and Professor Hayden would be familiar with this. And then that will lead us into a deep mathematical question for which no one knows the answer. And then I'll leave you guys off to solve the deep mathematical question. Here's the fundamental idea behind QBism. Ben Lev today asked me, how do you go against the charge of solipsism? You guys know what solipsism is? It's the view that you're the only thing in the universe, and everything else is your thought or your dream. And people often come up to QBists and look at their very meaning and say, you're a solipsist. It hurts. No, I'm not. In fact, my wife was the first one to give the best argument. Said, if you were a solipsist, you'd change the things. But you can't. That makes a fundamental idea behind QBism. The hypothesis that there is an external world not dependent on human minds, made of something, is so obviously useful and so strongly confirmed by experience down through the ages that we can say without exaggerating that it is better confirmed than any other empirical hypothesis. It's the fundamental idea. There is some stuff out in the world. What's stuff look like? Yes, it's cubes. There's some stuff out in the world. This is the fundamental assumption of QBism. But then there's this thing called the quantum state that we theorists and experimentalists use. And so what's the deal with that thing? What does it have to do with stuff? Well, remember Holmes. He said, I describe myself as a betabilitarian. I believe that we can bet on the behavior of the universe. This is the important one. In its contact with us. What are we betting about in quantum physics? It's not about what is out there, but what is happening when the world comes in contact with us. So let me put all of QBism in a cartoon, Captain QBism comics. There's Captain QBism, you see. And notice that Captain Cubism is wearing some goggles. Today, I walked into 2 labs. I had to put on 2 different goggles. It was exciting. How many of you wear goggles from time to time in your laboratory? Like almost everybody. You see, you too can be Captain Cubism. So there's Captain Cubism.
What wavelength did this value?
He might have.
I bet you haven't gotten that question before.
I never got that question. It's something. I hope it's the only one that's. All right, so here's Captain Cubism. This is a person who buys into the Cubist view of quantum mechanics. The idea is that a measurement, a quantum measurement that's described by a set of measurement operators should be thought of as not an observation of something, but should be thought of as an action that the experimentalist is taking on the external world. The external world being made of cubes, those are things that catalyze a reaction, catalyze a consequence or an experience for this agent. So an action is described by a set of operators. The consequence is described by choosing one out of it. And that is not recognized as, oh, something that's happening independently of the agent. The agent is deeply intertwined or entwined with what's coming about in the laboratory and in the world. Look, I mean, here, this is a physical system. I can take an action on it, and the action will have various consequences. Nothing greatly exciting here, but if it only had 3 legs, maybe it would have fallen over and spilled some coffee, and it might have done that, it might not have. I take an action on roads all the time, I take an action on the world when I cross the road, and I can't always predict the consequences. Consequences form me, whether I'll be run over or whether I won't. But my aim is to try to predict the consequences of various actions. And quantum theory is a formalism that helps us do that. I put this quantum state over here. Really, I should think of it as living in the mind of the agent, because it's the agent's way of calculating the probabilities for the consequences. So that's the picture. It's a very personalistic picture that an experimenter is actually taking an action on the world, or any person is taking an action on the world, and it will lead to things happening for that person, and their probabilities are about that. Now, just to make sure you understand the QBist point of view, here's what I want to do. I want to imagine that my marker here is an eraser. And I'm going to start erasing this agent out of the picture. Notice I call him agent, that's the word that we get from decision theory. I start erasing this guy, but I'm very careful not to erase the catalyst of the quantum system. That's out there. So I erase him, erase him, erase him. And here's the question I want to ask. From the point of view of QBism, what happens to this quantum state when I erase him? It goes poof. You really have to take this seriously in QBism. Without an agent, there are no quantum states. There is no such thing as the wave function of the universe. There is no such thing as a hydrogen atom being in the ground state in interstellar space without somebody doing a calculation about it. Wave function goes poof. But that doesn't mean that the rest of the world goes poof as well. I didn't erase the quantum system. It's still there. The rest of the world stays behind. But the use of the calculus is now gone. So the terms of the calculus is now gone. Maybe the best metaphor for thinking about QBism is this book by Leonard Savage called The Foundations of Statistics. It was the first book ever written on decision theory, statistical decision theory. And I often imagine that I have that book. I don't have it with me, but I have a different book, Phenomenology and QBism. Just tell your library about it. It's only $170. They've got some wonderful papers, one by a Stanford professor. So just imagine that this book is that book. And imagine that I walk up to a philosopher, be my philosopher. I walk up to a philosopher and I say, yeah, I just found this book on the shelf, Foundations of Statistics. And Professor Lev, the philosopher, says, what's that? It's about making better decisions. making better decisions. Yeah, it's something that I've been practicing. I've been using the techniques for it, and I find, for instance, I'm making better financial decisions when I'm betting on the stock market just because I'm using the techniques and so forth. But Professor Levy's a philosopher, and he knows that my hidden agenda is to say quantum mechanics is like this book. So I say, here, would you use the book? And it's like, oh, if you reached out. A philosopher would say, no, keep that at a distance. Because quantum mechanics is not like that. Maybe your financial yields have something to do with that, but not quantum mechanics. It's about the physical world. I'm like, well, what bothers you? The philosopher would go on and say, if you believe that, then you believe you're the only person in the world. No, I don't. This book was in a library. It was meant for anyone who walks up and pulls it out. They can use it themselves. It's a manual that I can use, you can use for making better decisions. So they might say, if we would ever do this, granted, I'll buy that. But physics should have as part of its task to explain where the user of the book comes from. And I like, well, look, in the beginning of Savage's book, it actually says, who can use this book? Anyone with a small knowledge of calculus and a piece of paper and pen. You can't find what it takes to be a user of decision theory from decision theory itself. And similarly, QBist would say you can't explain what it takes to be a user of quantum mechanics from quantum mechanics itself, because quantum mechanics is a version of decision theory. It's about how to gamble if you must. So QBism takes this idea seriously. We see that quantum mechanics, formal rules of quantum theory are in addition to this book, How to Gamble If You Must in a Participatory Universe. In a universe where when you push on things, they react differently than when you don't push on things. So this is the direction that I want to go in. There's this book by Savage. If he had written a second edition, he might have added an appendix, special considerations for decisions about love and marriage. He might have added another one, special considerations for when playing the stock market. Maybe appendix C is special considerations for how to gamble best when you're dealing with the physical world. So that's the idea. The formal rules of quantum theory are in addition to this book. It really boils down to this kind of idea put by the information theorist Dennis Lindley about De Finetti's idea. The topic study is the situation of an individual who is faced with uncertainty about some events of concern to him. All of us find ourselves in this position. De Finetti's task was the first to recognize this openly, that there's uncertainty all around us, and how best can we deal with it. The paradigm of De Finetti's view of probability is egocentric. It is a tale of a single world, single person contemplating the world and not wanting to be stupid. So here's the idea. Quantum theory is about not wanting to be stupid in this world that we're living in. Let me give you a mathematical sense of the idea. Here's how probability is defined from that notion. It's something called Dutch quantified. So probability is not yet defined. We don't know what probabilities are. But you can imagine that there is a bookie who has a table of numbers. And what these numbers correspond to is how much the bookie is willing to either buy or sell a lottery ticket for. So if the bookie puts this number up here, P sub E, it means that he is willing to buy this lottery ticket for any epsilon less than P sub E. And he's willing to sell the lottery ticket for any epsilon more than P sub E. That's the idea. So he has numbers on his board, and those numbers are the prices of lottery tickets. So let's look at this one, for instance, P of ERF. Well, that is the price that the bookie will be willing to sell a lottery ticket that's written as worth $1 if ERF. I don't have it written here, but that's the idea. And since we're talking about epsilons, we might as well say that these are the prices he's willing to buy or sell. Okay? This is not probabilities. These are just prices. Nothing to do with probability yet. De Finetti's genius was to realize that you could get all of probability theory from this notion by adding one rule, one ultimate postulate. And the ultimate postulate was that the bookie should never declare numbers on their board that will lead to the bookie getting a sure loss. So you can imagine that someone comes up and they say, oh, I'll buy so many E lottery tickets for this price that you say is a fair price. And I'll sell you so many not F lottery tickets for this price. And I'll buy some E or F lottery tickets for this price. If the prices aren't adjusted on the board correctly, so that, for instance, this law of probability when they're mutually exclusive, if they're not adjusted so that this is satisfied, then a gambler can walk up and take the house. So that's an example of being stupid, not having the prices adjusted so that they fit together according to probability theory. That was De Finetti's great idea. What it told him was that the way to read probability theory is as a normative rule. And that is because in any real world situation, not in your statistics class, but in any real world situation, you might get your probabilities for this weather pattern from a certain distance. And you might get your probabilities for another weather pattern from a different distance, and a third, and so forth. And then you ask, well, should I use those numbers for my gambling business? Well, you can do a quick test. Let me take all of the numbers that I'm reading from these independent sources and check whether they agree with this equation. If they don't, I know that something is wrong. I need to adjust some numbers. And I can't get the numbers from the newspapers, so I have to broaden my considerations to make sure that they fit together. In that sense, the probabilities that we write down depend upon the subject. They're subjective. And sometimes we have to work really hard and use guesswork and just raw guesswork in how we're going to get them. But we have, at the very least, make sure that they fit together according to this rule. This was something that guy, William James, emphasized, that the will is involved in making all probability assignments. So you see the word subjective, 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 and that's usually what causes most philosophers to reject this, because they're like, everything is subjective. Everything is subjective. But not everything is subjective. And here's the lesson to learn. The thing that Bohr said, if they just wanted to learn something. The norm is not subjective. That is specified by the world. You had better fit together this way, or you're being stupid with respect to the world. What's this have to do with quantum mechanics? QBism used quantum theory as applying extra normative rules to probability theory. So there's ones you just saw on that page, previous page. Quantum mechanics gives us something more. And that now is our scientific program. What is the more? It gives us, for instance, the motivation to try to understand the Bohr rule in purely probabilistic terms. The same thing for the Schrödinger equation. On a normal reading of the Bohr rule, we have quantum states, and we've got measurement operators, and we combine them according to this little rule, and then that gives us probabilities. On that way of looking at things, it looks like the rho and the e's are logically prior to the probabilities. Probabilities come from these more basic things. But if we want to view quantum theory as extra normative rules, we'd better get rid of this way of expressing things so that we can see that the essence is really a probability is related to some other probabilities in the right way. Idea I'm going to use, what I have, 15 minutes? 15 minutes. I'm going to use an idea from Richard Feynman, 1951. Feynman said the new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable. In these cases, one has to be satisfied with computing probabilities of various outcomes. But far more fundamental, was the discovery that in nature, the laws of combining probabilities were not those of the classical probability theory of Laplace. You wouldn't think that somebody would win a Nobel Prize for this theory, but it was the foundation of path-integral approach to quantum mechanics. This realization that, oh, what's fundamental is that probabilities are not combined in the normal way. And of course, he was thinking about the double slit experiment, where you can see a distinction between, well, what kinds of patterns you would get if you had detectors at 1 and 2, and what kind of pattern you would get if you didn't have detectors at 1 and 2. And you might think that these probabilities for this can be constructed from those, but it doesn't follow the normal rules. So he introduces amplitudes, and that fixes everything. But in a certain way, that distracts from what he said on the previous page. It's the rules for combining probabilities that's changed. His way out of it was to introduce something that's not a probability, but actually you can revive his original idea and make it completely general. So let me just show you about that. This is something I'm going to call the d-squared non-orthogonal slit experiment. That's just a word. What it really is a generalization of Feynman that goes this way. We have a quantum system. It's prepared in some quantum state, and it's going to travel through a measuring device that measures some observable of some variety. The measurement device, when it is turned on, generates outcomes, R sub I, and those occur with some probability P of Ri. And then the state gets modified generally as it goes through to something new, sigma I. And then that's going to head into another measuring device of some variety. And there will be probabilities for the outcomes of that measuring device and conditional probabilities for this one, given that one, etc. I'm going to claim that this picture, this little schema, contains everything that you ever needed to know about the Born rule. It's not just a single experiment on the double slit, but the way I'm going to make that clear is I'm going to apply some rules here. First rule is that this first measuring device is going to be something called a minimal informationally complete reference measurement. And this device over here can be any quantum measurement whatsoever. Notice how that contrasts with the double slit experiment. We had some measuring device here if we put detectors at 1 and 2, but that won't satisfy the rules that I was just saying. It wouldn't be an informationally complete measurement. And the other thing is at the slit, we only have one kind of measurement. We didn't allow a grading, for instance, so that we can grade and measure different observables. It was only one measure. In this picture, this is going to be an informationally complete one, fixed and special, and this is allowed to be any measurement whatsoever. Okay, that's the ground rules. But otherwise, there's a certain similarity. This measurement, when the switch is on, is like putting detectors at slits, and this measurement is like seeing where the particle gets at the backstop. But we allow any kind of measurement over there. Okay, what do I mean by measurement? Has everybody in this crowd had a quantum information course? Do you know that people in quantum information use this fancy notion of measurement called a positive operator value measure, or POVM? I'm going to assume you do. My minimal informationally complete measurement is a special one. The operators in it have to form a basis for the Hilbert space, the operators on the Hilbert space. And when I have a D level system, they have to have D squared outcomes. That's the ground rules. So there we go. Now, suppose I did this. I like erasers. Suppose I took my eraser and I erased this quantum state. It's gone. And I erase these operators in this box. They're gone. Erase that quantum state and that quantum state. And I'm left with a picture that looks like this. There's some black box. It gives rise to probabilities and conditional probabilities, but I've completely erased the quantum character of all of these probabilities. Intellectual question is, can I still say how the probabilities must be related to each other? That's the question. Can I still say how they have to be related to each other? And the answer is, of course I do. And they're related according to what's called the law of total probability. this thing down here. And that's just comes from Dutch book coherence. If these are probabilities at all, and I don't want to lose with probability 1, then they better fit together according to this. And now I'm going to introduce this little vector notation. Think of these as components of a vector. This is the components of a vector, and these are the components of a matrix, and let me write it that way. It's much simpler. Okay? But now, what if I turn off the switch and there's no measurement in the middle? So we don't have that picture. In fact, we've got this measuring device turned off. In that case, what happens is I've got a quantum state going in. It goes right through, and then it goes to this final measuring device. Now the Born rule is the only guidance that has for calculating probabilities. There's nothing like a Dutch book argument because there's no intermediate measurement that's happening over here. The Born rule looks like something different. It's not a relation between probabilities. Dun, dun. Is it? And in fact, it is. A simple manipulation, it's not hard to do, allows you to recast the Born rule for the situation where the switch is turned off in terms of the probabilities that arise when the switch is turned on. The only difference is this isn't the classical law of total probability that I had drawn here. There's an extra matrix inserted right between those two terms. So there we go. That is the Born rule. It's completely general. It works for any measurement E. There are no operators or state vectors in it, and there are no complex numbers. There's no amplitudes anymore. It's all disappeared. It's all about probability. Born rule, born again. Here's the way it is. The difference between this equation and the classical law of total probability is this extra matrix. And what we learn is that the probability on the left-hand side refers to one experiment. The probabilities on the right-hand side refer to a different experiment. So when quantum mechanics is giving us extra normative considerations, what it's saying is you had better relate your probabilities for one experiment to your probabilities from another experiment. And there we go. If you put it this way, then I'd say Feynman is right. In reality, that equation contains the only mystery of quantum mechanics. I think they're going to tell me I'm out of time, so let's come back. Let me come back to you.
Okay.
Okay, so let me just show one further thing. Old Born rule is obviously still visible in that formulation of it because this matrix of conditional probabilities, it uniquely specifies the measurement operators I'm talking about. And this vector of probabilities uniquely represents quantum states. And this is the old quantum probability that we had there before. But QBism gives us an attitude adjustment about how to think of that. We no longer think of, oh, this term is fundamental, and that term is fundamental, and this is derivative. QBism says you should read this normative. And just like in the other case, there's a subjective component in all of these things. You guys in the laboratory, you open up a piece of equipment and it says tested to this accuracy, and we find this and this. You open up another piece of equipment and you say, should I use the numbers that the company says, or should I test things myself? Should I readjust things myself? There's always a component of it. And now instead of the great philosopher William James, we now have the great philosopher Benjamin Lev in the picture. So look at that. Quantum mechanics consists of 3 subjective terms. But even from QBism, not everything is subjective. It's the relation between all of these that is the objective thing. And if we're looking for a statement of what's really powering reality, is it a universal wave function? QBism says no. But it would say whatever it is that puts that relation for the consideration of decision-making agents, that's what we need to be looking at to find quantum reality. Okay, I'm basically going to end the talk here. The part that I didn't tell you about, maybe I'll tell you some guys about it at lunch, is that once we write this equation, it invites us to ask, well, how distinct is the law of the Born rule from the law of total probability. You can pose a mathematical question, and you can answer that mathematical question, and it has a secret ingredient that I can't tell you about now. But that secret ingredient tells us what is the essential distinction between classical and quantum. And again, if you want to be looking for quantum reality is encoded in a normative statement. And if you found this essential distinction between classical and quantum, I think that it can be found in this equation. Now, that equation will tell you about the applications of these things. Secret ingredient. I won't tell you about the experiments, not that really. But it leads to a question of, does the secret ingredient exist? And no one knows whether the secret ingredient exists, but it's been found for a whole lot of quantum systems, just not an infinite number of them. And that secret ingredient ultimately turns out to be related to a very deep mathematical problem that's been around since David Hilbert when he posed his 23 turn-of-the-century problems. One of them is called Hilbert's 12th problem, and that just leads us to, now, why would the representation of Bohr rule that exhibits the essential quantities of quantum mechanics care about Hilbert's 12th problem? If I were to present this in front of a philosophical audience, what would the philosophers of physics say? Well, you don't believe what he's going to do. But a physicist might smell that there's an opportunity to learn something of very great importance from this new way of looking at quantum mechanics. And as I say, if any of you said, go it and go it stronger, we have a fellowship for you at my university. If you can be lured from stand. Thank you all.
Okay, so the classical version of Bohr's rule that you showed before comes from the fact that if I have some set of probabilities that spread the distribution, and I throw away the result of your measurement, that this is the probability that you get, summing over all of the conditional probabilities, right? And then when you have the Bohr's rule version, that's no longer true. Basically, if I throw away the measure, there's still fundamentally something separate from a subjective question of whether a measurement happened, right? Like if the magnetic detectors on the double slit experiment are on, it doesn't really matter whether the experimenter subjectively was able to see the result of which slit the electron went through. They still will see the distribution you get from the density matrix, done by putting it through QBism.
I'm not sure I understood the question, but let me just add this. So the language that you're using, got the detector on, I'm not in the laboratory. This is something.
No, you're in the laboratory. You still see the result of the second measurement. You just don't see the result of the first measurement.
So in QBism, there is no result of the first measurement.
Okay.
Doesn't exist. Unperformed measurements have no outcomes. And so you have to learn ways of talking about that are unusual for physicists. And in fact, we just put a paper on the archive just last month where we talked about how to describe decoherence in this crazy language that I'm inventing here. And it can be done. You just have to think differently. But one thing that you said was the Bohr rule that's when you throw away information.
No, I said the classical version is like.
Excuse me, the classical. This would be the classical version. I'd say, oh no, really what's premised here is the idea that there is an outcome. In the quantum case, in the middle measurement that's turned off, there is no outcome to condition on. So therefore something has to give. There's no conditioning. Now outcome isn't there. And the idea is we can still talk about the case where there is no outcome in the terms drawn from the case where there was an outcome, but we have to modify the laws of how to combine the probabilities.
Okay.
That's I can do.
I think I have some time to talk to him after this.
Sure.
Do we have any other questions?
Okay.
You and Eddie.
So in the quantum version of the Bohr, you define the in the quantum version of the Born rule, you define the Born matrix by an inverse. Is there any interpretation, like how can you be sure that that inverse is it's always invertible? What does it mean if it's not?
Yeah, I rigged it so that it would be invertible. And the way I rigged it was I said that this thing is a minimal information complete measurement, and that causes the Born matrix to be invertible. Can take care of the cases where it's not invertible, but then you have to introduce pseudo inverses. You have to be careful. But the result is the same. And the result is that particular form, but it also allows us to explore this question of what reference measurement should we choose so that this becomes as close to the law of probability as possible. And that allows us to get a unique answer modulo whether the ingredient exists or not. That's the tough matter. Yeah.
Oh, thanks for the talk. Could you comment more specifically on how decoherence works in this model?
Yeah. Boy, that's tough. And genuinely, it's a tough one. I'm not belittling it because that was something that we never really felt comfortable with for like 10 years until a big struggle, intellectual struggle last year. And we just put the paper on the archive. It's titled Quantum Dynamics Happens Only on Paper. So, which is a tough thing to stomach. There's a lovely paper actually by Bill Wooters. Who knows the name Wooters? Everyone in quantum information should know the name Wooters, but you guys are so young. These founders, these great founders of our field are starting to get forgotten. Wooters had a paper in the late 80s where he toyed with the idea of having a physics that only had, in essence, measurement outcomes in it. No unitary dynamics at all. And in the introduction to the paper, he says it's sure hard to think. It's sure hard to think of unitary dynamics as not being there because it powers everything that we do. In this paper, I'm going to take this crazy point of view where there's only measurement outcomes in some sense, branching events. So this is kind of, in essence, how we tackled it in this other paper. And what we do is actually starting with you have to think about the ways that you got in the backwards thinking. What's your name?
Henry.
Henry. We have to ask questions like Henry was asking, and ask how would we tackle that. So the kind of language that Henry might have been using was that there really was, the photon was emitted or not, we just didn't register it, etc. We've got to get away from it. Instead, we ask this question, I've got to gamble now. Somebody is telling me, gamble now about what measurement outcomes how you will gamble in far future. I'm going to gamble now about some experiment that's going to be done in the far future. And how do I do that? And we say, well, you've got to analyze how you would gamble from your standpoint now and your standpoint later, and how are they connected? And the thing that we end up focusing on is, can I identify anything that I could do in the future? In the middle, in between in the far future. Is there anything I could do in the middle that wouldn't affect how I'm going to gamble now? And when you identify that, then there's normative rules, put it all together and get it. But it's only happening on the stock fellows spreadsheet. That's the short version. Okay. I'm not practiced at giving that explanation, but we just
Thanks. I'll take a look at the paper. Thanks. Experimentalists, think about it.
Okay.
Thanks.
Maybe one more question.
So when you say like an observable that wouldn't matter, is that sort of equivalent to like the fact that, okay, when I don't view this as a measurement that I'm throwing away the results, then it's equivalent to like I get entangled with all the degrees of freedom in the detector, and then those can't matter for.
I think that you would say, well, the standard explanation is that there's all this entanglement with the environment and so forth, and that's really there. We're just playing a game where we say, no, that's not really there. What's really there is the fact that it doesn't matter to me. That's what's really there. And by the way, this idea of Wooter's, part of this is an attempt to say, okay, quantum states are not real. Ultimately, dynamics decoherence is not a real thing. It's not a factual feature of nature. This leaves us with one thing that could be real, and that's this idea of Wooter's, essentially, that it's the events. The events are the real things in the world, and all the rest of it is under some calculations on paper.
So when you say it's just the events, I guess through this whole talk, there was an implication that there is some underlying physical thing, and then the laws of quantum mechanics are like a mix of like what the underlying thing evolving looks like with knowledge about it. Do you have a description for what the underlying thing evolving is? And also, does it have local laws?
This is why philosophers of physics hate us, and other things. Because, for instance, one of the guys that I made fun of, I'll tell you one more story. Sorry, one more story. I used this slide at Gilla. Eric Cornell was in the audience. And then after my talk, he wanted me to come to his office. And he goes, can you name the philosophers that you showed on your slide? And so I told him names of all of them. He goes, oh, I don't know any of them. I don't know any philosophers. There was one philosopher who impressed me, Ian Hacking. And I go, oh, Hacking is a wonderful philosopher. And Eric Cornell goes, oh, so they're not all bad. Oh, okay. So there's one in the list up there, a guy named Tim Maudlin. And I remember an interaction with him once. He says, tell me the ontology. Tell me what's the real stuff in the world. Right. Or there's nothing to say. Cubism, I would say, is a very careful, methodical program. We're slowly getting to the answer. And so therefore, I'm going to tell you, no, I can't answer you yet, because that's part of the research program. Part of the research program is to see what the real stuff is and how it implies this modification to decision theory. It's an appendix C of 17.
Okay, thank you. Thank you all. It was a great place.